Hello everyone, welcome back to my YouTube channel. So today we are going to discuss about important system design terms that everyone must know. This is part 3 of this series. We have already discussed these terms as part of part 1, core network and architecture concepts. All these items, client server architecture, IP addresses, DNS, HTTPS, REST, APIs, proxies, reverse proxies, and API gateway. Okay, and we have discussed these terms as part of part 2, data handling and communication, caching, queues, message brokers, rate limiting, throttling, latency, and load balancer. As part of this video, we are going to discuss about databases and storage related terms in system design that we mostly use. One is database indexing. We are going to discuss about this. Database sharding, replication, blob storage, idempotency, and eventual consistency. So we are going to discuss about all these terms as part of this lecture, and in the later on we are going to discuss about all these items. So cap theorem, so there is some relationship between eventual consistency and cap theorem. We are going to discuss a little bit about this as part of this lecture, but mostly we will discuss about this in detail, cap theorem and all these terms, in the next parts, right? So let's first see database indexing. Database indexing is like creating a shortcut to quickly find the data in a large table. It speeds up search operations by creating a data structure, often a B tree, that helps locate records without scanning every row, right? So for a real world example, you can say that imagine a library without a catalog. You would search every book to find Harry Potter, but with an index of titles, you directly go to the bookshelf. Similarly, when you run this query, let's say select star from users, where email, okay, this column, email is equal to a@b.com. Okay, so if you used indexing on this one, okay, and index on email column, it allows instant lookup, right? So it is used in e-commerce search, searching product names, login systems, email lookups, filtering dashboards. All right, so how does this indexing work? So when you create an index on a table column, the database creates a separate data structure, commonly a B tree or hash table, that stores the column value along with the pointers to the actual rows in the table, right? So we are not going to scan the complete table. We are just going to search in that particular column, and when we are going to find that value, we are simply going to return that. Okay, so here consider a table employees with millions of rows. Select star from employees where employee ID is 123. So without an index, the database performs a full table scan. Okay, with an index on employee ID, it directly finds the row using the index, okay, significantly faster, right? So this is nothing but database indexing. Now let's discuss database sharding. So sharding is nothing but it is a process of splitting a large database into smaller pieces called shards, where each shard holds part of the data and each shard runs on a separate server, right? So for a real world example, you can say think of a big spreadsheet too large for one file. Okay, so you divide it alphabetically. Let's say A to F in file 1 and G to L data is in file 2 and so on, right? So in practice, Instagram shorts users based on the user IDs. Okay, so user 1 to 1 million, let's suppose their data is on DB1, 1 million, 2 million users are on DB2. Okay, so it is used in high scale apps like Instagram, X, banking systems, okay, to partition accounts by ID or region, right? Okay, now what are different types of sharding? So horizontal sharding, row based. So rows are distributed across shards, most common and typically referred to as just sharding. Okay, vertical sharding means column based. So different tables or columns are split across databases, like orders details is in one DB, customers detail is in other DB, right? Something like that. Then there is range based sharding. So data is divided based on the value range, data range, like user underscore ID range that we were using here, right, based on user IDs. So this is one type of sharding. Then hash based sharding. So hash function is applied to the shard key to determine the shard, so ensures uniform distribution, avoids data skew, right? Then geographic directory based sharding, like there is a data, okay, of many users. So let's say I'm keeping the India data in India DB, I'm keeping the data of US people in US DB. Okay, so data is sharded based on the geography or region. India users in one shard, US users in another. Okay, so this is nothing but data sharding. Okay, database sharding, right? Now let's see the third term, replication. So replication means copying data from one database server, which is going to be your primary, to another secondary to improve the availability and fault tolerance, right? So in for the real world example, you can say if you back up your photos to Google Photos and also iCloud, you are replicating them, right? So in tech, if DB1 fails, DB2, which is a replica, takes over, ensures zero downtime, right? So it's not like you are searching for a score of a live match, right? And there is one application in that there is some issues, okay, in one DB, right? You are searching for some player data, let's say. So there is some issue, so they are going to use some other DB, right? Replica DB. From there you can fetch the information, right? So this is the example, right? So it is used in master slave databases, cloud hosted services, AWS RDS, multi AZ, and real-time dashboards, right? So how does this replication work? So there is a primary database, source or master, and one or more replica databases, secondary slaves. So changes made to the primary database are copied to the replicas. Replicas can be read only or sometimes read write depending on the replication mode. Okay, so this is about replication. Now next term is blob storage, very important term, right? All these are very important actually. All this database replication, database sharding, database indexing, all these terms are very important. Okay, now let's see blob storage. So blob means binary large object. It is used to store unstructured data like images, videos, PDFs, etc., which don't fit well into the rows and columns of your relational database, right? So a real world example, when you upload a profile picture on his Facebook, it's stored in a blob storage like AWS S3, and only the link path is stored in the user table. So it is used in file uploads, media streaming platforms, document storage, backups. All right, now how does this blob storage work? So blob data is stored in containers, and containers reside inside the storage accounts. Each blob can be accessed using a unique URL. Blob storage supports HTTPS access, making it great for web apps, mobile apps, and backups, etc. So, real world use cases, you can say media streaming platforms, YouTube, Spotify. So, store videos, thumbnails, audio, right? E-commerce, store product images, brochures, customer documents, then backup and disaster recovery, long-term storage of data, snapshots, big data, store input output files for analytical jobs, right? AIML, store training datasets, model files, then IoT, store sensor logs and binary data from devices. Okay, so this is nothing but globe is nothing but binary large object. Okay, all right. So there is one more term, CLOB. So if you know about that, just write the answer in the comments. Okay, if you know what this is, what is CLOB and what is the difference between BLOB and CLOB. All right. So now here, let's see these examples of cloud blob storage providers. Okay, so Microsoft Azure, okay, Amazon AWS, Google Cloud, Oracle Cloud, IBM Cloud, right? So now let's see the fifth term, okay, idempotency. It's very important term, right? So what is this? An operation is idempotent if performing it once or multiple times gives the same result, right? So actually this is very important, right? So if you click pay now on Amazon twice due to slow internet connection, the system should ensure only one payment is processed. Okay, so that's why it is very important, right? So an idempotent API like put user 123 ensures that the same user is updated no matter how many times it's called with the same payload. All right, so it is used in payment systems, retry mechanisms, RESTful APIs, put, delete are expected to be idempotent, get also, right? So you can say think of a light switch, okay, real life analogy. So turning the light on and then pressing on again doesn't change anything, okay, it's idempotent. But a toggle switch on is not idempotent. Okay, now technical definition, you can say in programming and networking, an idempotent operation can be repeated safely without causing unintended side effects, right? So here get operation, it is idempotent, always retrieves user with ID 1. Delete, it is Repeated deletes are safe now. User is already gone in one delete, right? Post order, no. Repeated calls create multiple orders. Okay, so this is not idempotent. Now this put users one, yes. Replaces user data, same data, same effect. Okay, now where is idempotency important? So in REST APIs, okay, so it ensures safe retries on network failures. Put, delete, and get should be idempotent. Post is not idempotent by default. Okay, note this point. Now payment systems to avoid duplicate payments. If a user retries after failures, then distributed systems, so it prevents inconsistent state during retries, okay, due to crashes or timeouts, right? So now last term, eventual consistency, right? So in distributed systems, eventual consistency means all nodes will become consistent over time, but not immediately after an update. Okay, so a real world example, let's say if you update your profile pic on Instagram, your feed might show the old one for a few seconds before it syncs. That's eventual consistency in action, right? So it is used in Amazon DynamoDB, Cassandra DB, or distributed caching, then large scale microservices, right? So real world analogy, you can say, imagine group chats in messaging apps. You send a message, it appears instantly on your phone, right? But it may take a second or two to appear on your friend's phone if their internet is slow, right? So eventually everyone sees the message. So this is called eventual consistency, right? So now how it works? So when data is written to one replica, that replica responds immediately, fast, right? Other replicas are asynchronously updated. So during this lag, readers may get stale data, right? So eventually all the replicas reflect the same final state in the end. Okay, so now we are going to discuss about this in detail in our next video, right? What is cap theorem? So but let's see the relation between them. Okay, cap theorem and eventual consistency. According to cap theorem, in a distributed system you can only guarantee 2 out of 3: consistency, availability, partition, tolerance. Okay, only 2 out of 3. So eventual consistency favors availability and partition tolerance at the cost of immediate consistency, right? So eventual consistent use case, you can say e-commerce product availability. Small delay is acceptable, right? Social media likes, comments. Users don't expect a real-time synchronization, right? Inventory systems acceptable for large-scale retailers, right? And read-heavy systems, CDNs, content delivery networks, mostly reads, fewer writes. Okay, tolerance delay, right? So that's all as part of this part 3. So we have discussed all these terms. Now in the next lecture, I'm going to discuss about cap theorem, consistent hashing, microservices, scalability. Very, very important term, this scalability, right? Microservice, very important. This cap theorem, very important. Redundancy, fault tolerance, very important. Heartbeat mechanism, reader election, circuit breaker pattern. Okay, all these terms are actually very, very important. Okay, so we are going to discuss all these terms as part of our next lecture. So I hope that you guys are clear with all these terms under these databases and storage. And if you guys still have any doubts, then please feel free to ask in the comment section. Meet you guys in the next video. Thank you. Bye bye.